Okay, today we're going to talk about the second half of our chemical kinetics lectures, and we're going to be talking about various aspects of chemical kinetics. First of all, a little bit of review. We ended last week talking about first order reactants. And in a first order reaction, or one that proceeds in a first order rate, if you plot the natural log of the concentration of the reactants over time, you'll get a straight line that looks something like this. And so what we do with that is we iterate that mathematically to relate these concentrations to time. And with the first order reaction, we, as I said last week, if you take the natural log of the concentration at any time t and over at the concentration at time 0, that is going to be equal to the negative reacting constant times the time that you've selected. Now, in order to get rid of this negative sign, you can invert this fraction so that the natural log of the starting concentration, which is this concentration here, divided by the concentration at time t, let's say 12 hours, that's going to equal to the reaction constant times that time, 12 hours. And this is a linear plot in the natural log sense. So the linear relationship between the natural log of the concentration of the reactant and the time shows that the decomposition of hydrogen peroxide is a first order reaction. Now, these first order reactions can sometimes take this sort of, if you simplify it, you can see that sometimes they can take this sort of look. In other words, if you take this equation right here, and when you multiply both sides of the equation by the natural log of AT, and since it's the natural log, when you multiply, it's added instead of multiplied. If you do that, you get an equation that looks something like this. And I'm just putting this underneath there to show you that this is, if you remember Algebra 2, that a linear equation will fit the following formula: y is equal to mx plus b, where b represents the y-intercept and m represents the slope of the line. Now this curve right here, you'll notice that it's not exactly a straight line. And because it's not exactly a straight line in terms of the natural log of the concentration versus time, it's not really a first order reaction. So what sort of reaction is this? Well, if you take something like this that does not have first order straight line, and you instead you plot it as 1 over the concentration and you get a straight line, then this is what's known as second order. And second order states, as you remember, that the rate is equal to the rate constant times the concentration squared, so that 1 over t, concentration at time t, is equal to kT times 1 over the concentration at time 0. And so these two graphs show first and second order plots. This is a first order plot because it's a natural log plot, and this is a 1 over the concentration plot, so this is a second order plot. And since the first order plot is not linear, then the reaction is not first order. But because the second order plot is linear, this indicates that the kinetics for this reaction is a second order kinetics. So if you have 1 over the concentration times time versus time, and you get a linear plot, you know that it's a second order plot. This is the plot for butadiene dimerization to form octene, and you can see that it's a linear reaction, linear second order plot. So here's a problem. If you have the reaction is second order and the rate constant is 5.76 times 10 to the minus 2, if the initial concentration is 0.2, what is the concentration after 10 minutes? Okay, well, let's take a look at how we would go about doing this. And let me pull up my plot thing so I can do that, my writing program so I can do that. So, with this, we know that 1 over the concentration of A equals kT plus 1 over the concentration of A at time t. Or time 0, excuse me. This is time t here, sorry. And from this problem, 1 over the concentration of A at time t is equal to, and this is given as 5.76 times 10 to the minus 2. And the time that's given is 10 minutes plus 1 over, and the initial concentration is 0.2 molar, so 0.2. So this is going to equal 0.576, because you multiply that 10, plus 1 over 0.2 is 5. So this is going to equal 5.576. And that's 1 over the concentration at time t, which times t is 10 minutes. So if we find AT concentration, or A at 10 minutes concentration, it's going to equal 1 over that. If you do that math, you get 0.179 moles per liter. So that's the concentration at the time given. Now this slide right here shows zero order kinetics. Now notice we're just plotting the straight concentration. It's not 1 over and it's not the natural log. And when you plot the straight, if you get a straight line with just the plain concentration, then that means it's 0 order. If you get a curve like this, it means it's first order, and if you were to plot this on a logarithmic scale, you would get a straight line here, but then this one would become curved. And in 0 order kinetics, the formula is AT is equal to K minus KT plus A0. So the decomposition of ammonia on tungsten, which is given in this straight line here, is a first order or 0 order equation, whereas on quartz or silicon dioxide, which is shown here, it's first order. Now here's a situation where you start out with 1 molar, and over a period of time you'll notice that it goes from 1 molar to half molar to quarter molar, etc. 6 hours, 12 hours, 18 hours. Well, this is an example of a half-life. In other words, the time it takes for half of the reactants to disappear is known as the half-life. And so the half-life here is 6 hours. So after 6 hours you have half. After 6 more hours you have half of what you had at 6. After 6 more hours you have half again, and so forth. For a first order reaction, if you do the mathematics for using the previous equations and solve for t, the half-life is going to equal 0.693 divided by the constant. Now, in your book, it goes through this derivation, and you can do that if you want, or you can just remember this equation. For a second order, the half-life is 1 over K times the concentration at time 0. So this shows the decomposition of hydrogen peroxide at 40 degrees, and the color decreases as the hydrogen peroxide is destroyed or decomposes. So the two equations you need to remember are this one and this one. So let's do a couple of problems looking at half-lives. The first problem says the first order radioactive decay of iodine 131 has a rate constant of 0.138 per day, or day to the minus 1. what is the half-life of the radioactive decay of iodine? To do this, we know that the half-life is equal to 0.693 divided by K. So in this case, it's 0.693 divided by 0.138. And if you do the math here, you get 5.02 days, or let's say 5 days. Well, let's say 5.02 days. Now let's look at the second problem. Calculate the rate constant for first order decomposition of hydrogen peroxide. And this came right off of the slide. So it wants you to calculate the rate constant given this data that was on our previous slide, this slide right here, where every 6 hours it decreases by a half. Well, you use the same, it's first order, so you use the same equation, but in this case, you solve this equation for K, and it's going to be 0.693 divided by the T1 half, and the T1 half was 6 hours. And so you put that in, and when you do the math here, you get 0.116 day minus 1, or hours minus 1, excuse me, hours minus 1. Now this slide, we're moving on now to something called the collision theory. And this slide shows how the collision theory explains the reaction of various molecules and why the rate of reaction is affected by various things, including the temperature and the concentration. Here we have illustrated two different ways in which two molecules can collide with each other. In the top you have the carbon monoxide molecule where the oxygens collide with each other. Now, since there's no open bond on that oxygen, there's no reaction. The bottom shows a collision where the carbon collides, and because there is a possibility of bonding with the carbon, then it is possible for that oxygen to become detached and attached to the carbon and leave a single oxygen to bind with another carbon monoxide molecule. Now, if you look at this diagram carefully, you can see that why temperature, for example, would affect the reaction rate. Obviously, when you increase the temperature, you're going to increase the speed in which these molecules are flying around, and if everything else is equal, with an increase in speed, there's going to be more collisions, just a bulk more collisions, and there are going to be more possible opportunities for the bottom collision to occur. Similarly, if everything else being equal, but you increase the concentration of either reactant, again, you increase the likelihood of the proper collision occurring and leading to the reaction, the desired reaction. And so, in many cases, and then thirdly, another example would be surface area. Let's say, for example, and this isn't the case with this reaction, but let's say, for example, you had particles or gravel versus a single solid block. You would see that the exposed molecules that could undergo collision is increased with increased surface area, and so these collisions are more likely to occur. Whereas if the surface area is decreased, all of the molecules that are in the middle of a solid block are totally unavailable to collide, and so it's totally impossible for them to undergo a reaction. So this sort of diagram helps to illustrate how certain things do affect the rate of reaction.